Okay, so going back to S sub P, the skin factor caused by the perforation. As I told you, it could have three terms. The first one is S sub H. What is S sub H? It is the plan flow effect. S sub H is calculated by ln RW divided by RW dash. What is RW dash? This is the effective wellbore radius. Okay. This model says that there should be some change in the wellbore radius. The wellbore radius going to be what? The wellbore radius will be RWA will be more than RW, greater than RW. So ln RW divided by RW dash will be always less than 1. Then we can calculate as a sub h. Okay, so a sub h in this case will be always negative. It's not positive. It is always negative because RW dash always greater than RW, except for theta equal to 0. Now, how can we calculate RW dash? RW dash calculated by two models. When theta, the phasing angle is 0, so RW dash is calculated by this model. The perforation length tunnel, the length of the perforation tunnel divided by 4. When the phasing angle more than 0, then we could go with this model. What we have here, A theta. A theta is taken from this table. See, this is A theta. Depending on what? Your phase angle. Okay. RW, this is your actual wellbore radius, and this is the perforation length. Okay. This table is given by Karakash and Tariq, 1988. Karakash and Tariq, 1988. So this is the way to calculate a sub H, the first term of a sub P, the skin factor of the perforation or the cased hole completion. Now we need to go to the S sub V. What is S sub V? This is the vertical convergence effect. As I told you, this is your perforation here, and the flow is going to be the flow going to be horizontally, but it could be like this or it could be like this. There will be some convergence for the streamlines, and always, if we have this type of convergence, there will be more pressure drop. So S sub B is calculated by what? S sub B is calculated by, here is the model for S sub B. See, S sub V is calculated by this model, and S sub V, this could give the major contribution to S sub P. The major contribution is given by the vertical convergence effect. The major contribution to what? To S sub P, the damage caused by the perforation. And this one is calculated by this model. Tan to A, H sub dB minus 1, RD sub B. What is A? A is calculated by this model. What is B? B is calculated by this model. What is H sub D? Here is H sub D. What is R sub D? Here is R sub D. And we have A1, A2, B1, B2, taken from where? Taken from the table given by Karakash and Tariq, 1988, the one shown in the previous slide. If you look carefully at H sub D and HR sub D, what can you tell me? What is the part here, guys? Do you see the one here? What is the main part here, guys? See, what is that? Can you please give me some feedback for this term? What this term is called? What is that? Do you remember, one of you? when we have been talking about horizontal well, the performance of horizontal wells. You remember, guys, the square root of KH divided by KV? What is the term used to describe this one? Who can remember that? Is it the anisotropy? The anisotropy. Now, when KH, when the horizontal permeability is the same for the vertical permeability, the square root will be 1, but we still have the rest of the models for H sub D, R sub D. So now we know how to calculate S sub H, the plane flow effect. We know how to calculate S sub V, the vertical convergence effect. Now we're going to go with well-bore effect. The well-bore effect is calculated by this model. See, this is the model for well-bore effect. So the skin factor of the well-bore, SWP, C1, C2, RW2, C2, RWD. What is C1, C2? Both of them taken from the table given by Karakash and Tariq, 1988. While RWD is RW divided by the length of the perforation plus RW. Okay. So for S sub P, we just need to follow the mathematical models and get the value of S sub P. Okay. While S sub C and theta, we just need to use the tables given by Simcoli et al. 1975. Okay. These are the three. Types of the skin factor: S sub D, S sub C plus theta, S sub T. And then the last one is the summation of S sub PS. This is the pseudo skin components. This one gives you the skin factor caused by the non-darcy flow, multiphase flow, the convergence where? Near the wellbore. This is called the choke effect. The narrowing in the cross-section area when the fluid is going to move from outer part of your drainage area to the part close to the wellbore. It is called the choke effect or convergence effect close to the wellbore. Now, for the non-darcy flow, guys, as I told you at the beginning, most of the oil reservoir, we could assume that the flow could follow darcy law. Most of the gas reservoirs, we could assume that the flow could follow non-darcy flow. Okay? What is the difference between darcy flow and non-darcy flow? Non-darcy flow, there is a term for the pressure drop caused by non-darcy flow, suggested by who? By Forkheimer, 1901. Forkheimer developed Darcy law to consider the pressure drop caused by non-Darcy flow. What I'm saying? So he put two parameters. If you remember, guys, when I talked about the reservoir performance, the last part of the reservoir performance, before talking about horizontal well performance, I have talked about the non-Darcy flow. If you remember that, if you go back to my notes of the reservoir performance, you're going to find more details about non-Darcy flow. So Forkheimer developed the flow equation based on Darcy law, and he said the flow equation of Darcy law should consider the pressure drop caused by non-Darcy flow, and he said that the part of non-Darcy flow can be calculated by beta rho v square. Beta rho, if you remember, v square. And beta, this is the inertia constant. The inertia constant. When we have non-Darcy flow, the velocity is going to increase, and the inertia force is going to increase. Then we will have more pressure drop caused by non-Darcy flow. Beta. Beta is calculated by a lot of models. You can find them in the literature, tabulated in the literature. One of them, again, there is a textbook written by Economides also. You can find the table for beta. Beta is a function of what? Porosity and permeability. Rho is the density, and V you can change, you can convert V to flow rate Q. Okay. Then the term B rho V square can be written in terms of what? dq square. If we remove dq times q, so we are talking about dq is called rate dependent skin factor. Rate dependent skin factor. See what I'm saying? So basically, the skin factor, the total skin factor, is the skin factor caused by Darcy flow and the skin factor caused by non-Darcy flow, given by what? Rate dependent skin factor, that is dq. See? So the apparent skin factor is the skin factor of Darcy, the one that we have been talking about starting from our class, and the skin factor caused by non-Darcy flow, that is rate dependent skin factor d sub q. See what I'm saying? So this is the first one. The second one, multi-phase flow effect. Guys, as you know, right now we have the inflow performance relationship for the single phase flow oil. We have the inflow performance relationship for gas flow, okay, single phase flow gas, and we have some of the models for inflow performance relationship when we have multi-phase flow. Okay. As a general statement, whenever we have multi-phase flow, there will be more pressure drop. Whenever we have multi-phase flow, there will be more pressure drop. And again, going back to the same concept, whatever the additional pressure drop, the required additional pressure drop, we can call it skin factor. Okay, there is a pressure drop required by the flow itself. I'm not talking about this one. I'm talking about the pressure drop required more than the one that can be calculated by the regular flow of fluid in the porous medium. The one that can be calculated by the Darcy law, or the inflow performance relationship without skin factor. This is the ideal pressure drop. Whatever the pressure drop more than the ideal pressure drop, this would be part of the skin factor. How much, if you ask me how much I could agree with this fact, I'm not totally agree with this fact. The reason for using a skin factor, guys, always the reason for using a skin factor, when we couldn't understand some of the natural phenomena, we could give it like a factor. We do not have really good mathematical representation for the physical phenomena. So we could say, okay, we can describe this one by a factor. So skin factor is one of them. Now, okay, now good. We know how to calculate. We know how to calculate S sub D. Let me say S sub C, S sub theta, S sub P, We know how to calculate rate dependent skin factor. We know how to calculate the total skin factor. This would be fine. Okay, we can do it. And as you know, guys, we do not rely on one technique to estimate one of the parameters. So do we have some other techniques to estimate skin factor? Yes, of course. Yes, of course. Skin factor can be estimated, can be calculated by well-test analysis. From well-test analysis. Next year, hopefully next year, guys, you know, I'm teaching what? I'm teaching well-test analysis. Okay. So next year, this kind of technical elective, or, as you know, next year you may enroll with me for the test analysis, and you will know how to calculate the skin factor either from the drawdown test or the pressure build-up test. Okay, I do not need to go with the analytical models for the calculation of skin factor now, but you will have more details for calculating the pressure drop, or for calculating the skin factor and the pressure drop caused by skin factor using the well test analysis.
I know that, Hojam.
Fatih, are you taking this one with me?
Yes, Hojam.
Okay, good. So you know, as you know, Fatih,
Yes, Hojam.
we have nothing to do more than how much is the permeability, how much is the skin factor, how much is the thermal storage effect. So the reason for that, because skin factor is really important. It could change. It could change the performance. As you know, at the beginning, when I explained the fold of degrees, the fold of increase in the productivity index because of the skin factor. If we have skin factor +2, or if we have skin factor -2. So skin factor is important. It is important. Okay. So right now I am done. If you have questions, please ask me. Otherwise, I am going to assume everything is clear and very well understood, and there is no troubles.
No questions, Hojam. Thank you.
Okay. Now listen to me. I just finished the theory part. Now we are going to go with the example that shows how to calculate the skin factor. Okay. So now I'm going to upload and share the Excel sheet with you, and then we are going to work together for solving the problem. Okay. So if you do not have questions, I'm going to go for stop sharing the slides, and I will share with you the Excel sheet. Okay. So let me go. Okay. Where is that? Yes, I think this one. Yes. Okay. Yes. Here is the one that we could have, guys. Okay. So what we have basically, it is given to us that the formation thickness is 50. See what I'm saying? 50. RW is 0.5. Theta, the inclination angle, the deviation from the vertical direction is 15. ZW 25. See, ZW 25. HW 25. What does it mean, ZW 25? The vertical distance measured from the bottom layer to the midpoint of the perforated section is 25 feet. Okay. Now the vertical direction of the perforated section, HW 25 also. The radius of the perforation 0.25. The length of the perforation 1 foot. I mean, this is for the tunnel. The height of the perforation, okay, 1. Horizontal permeability 20, vertical permeability 8. The phasing angle 60. This is phasing angle. S sub D, it is given to you. The S sub D, what is S sub D? Mechanical skin factor and the skin factor caused by injection, if there is injection, and the production, 0.5. And the summation of S sub PS also is given to you. That is what? That is the non-Darcy flow, the multiphase flow, and the convergence or choke effect. It is given to us 1. The viscosity of the fluid given to us 2. Oil formation volume factor given to us 1.125. The radius of the drainage area is 1,500 feet. Okay, good. Now, what we need to prepare some of the things for us. Okay. We need to calculate, guys, as you know, we need to calculate H sub D.
I'm sorry for interruption. Can you please share this Excel file so that we can follow you and solve together?
You mean you cannot see the Excel sheet?
No, hocam, I can see.
Oh.
I just wanted to share the Excel file with us so that we can follow you and solve together.
Yes, that's my question. Do you mean that you cannot see the Excel sheet now?
I can see, hocam.
You can see?
Yes.
So what do you need me to share with you? What are the things that you need me to share with you?
I mean, can you please send this Excel file to us?
No. I will upload the Excel sheet to AutoClass, and you will have it probably this week. But now I need you to give me your attention.
Oh, okay.
Okay. So now H sub D. What is H sub D? Listen, guys. What is H sub D? H divided by RW. So I'm gonna say what? H. This is H divided by RW. This is RW. Okay. So how much H sub D? 100. Now I need to get what? ZW divided by H. See? ZW divided by H. Where is ZW? This is ZW divided by H. This is H. So how much? 0.5. Good. Now I need to calculate HW divided by H. How much HW is this? Divided by H. So we are good. Now we have all the parameters that we need to calculate what? S sub C and S sub theta. The table given by Simcoli et al. Now I'm going to go to the tables. Here are the tables. See? What I need to know, let me make it bigger so it could be clear to you. What I need to know, I know that the phase angle, this is theta, see? Theta, this is the, this is the, theta is the deviation angle, see? How much the deviation angle for our case? 15, see? 15. So we have 15. Good. And what else? We know that HD is 100. Okay. ZW by H, it is 0.5. So this is 0.5. And HW by H is 0.5. So we have to go where? Here. So this is our case. See? This is our case, guys. See? Is it? Is that clear? Is that clear, guys? This is our case. See? The deviation angle is 15. Deviation angle is what? 15. HD 100. This is 100. ZW by H 0.5. This is ZW 0.5. I think it's 0.25. Sorry, I think it's 0.25. So we should be where? Here. Sorry, this is the one that we are looking for. Here, see, guys, is that clear so far? 100, 0.5, 0.25, and 15. Let me check. See, 100, 0.5, 0.5, 0.5. Sorry, 0.5, 0.5. 0.5, 0.5. And then get back here. So yes. 0.5, 0.5. Is that clear so far, guys? Is that clear? Is that clear?
Yes.
So
It's
now
clear.
S sub theta minus 0.175. S sub theta, see? S sub theta. Could take some time. S sub theta. This is S sub theta. Let me make it small a little bit. So S sub theta what? Minus 0.1, how much? 0.175. Is it 0.175? Yes, it is 0.175 minus 0.175. So minus 0.175. See? Now I need to calculate what? S sub C. S sub C, guys. Okay? So S sub C is what? S sub C is, see, 2.369. 2.369. 2.369. 2.369. Then I need to calculate what? S sub C plus theta. See what I'm saying? S sub C plus theta. See? This would be what? This would be this one plus that one. So we are done now. We got the skin factor caused by partial completion and the deviated holes. So let me highlight this one by yellow. Good. Now, what is the second that I need to calculate is S sub P. What is S sub P? S sub P comes from what? S sub P comes from SH, SV, SWP. So I need to calculate now what? I need to calculate S sub H. See? See? I need to calculate S sub H. To calculate S sub H, I need RW dash. To calculate RW dash, I need to know how much is A theta. A theta is taken from where? The phase angle. Taken from where? The table given to you. Which table? This is the table. What we need to know? We need to know the phase angle. How much the phase angle given to you? 60. So from this table, what I need to have some of the parameters. So I'm going to put them here. So what I need, let me take it from this one here. So I could put here just to be. So this is A theta. A theta, guys. How much A theta? See, this is 60, guys. It is 0.81 theta. See? Now what? A sub A1. How much A1? Minus, just please give me your attention. Okay. And now A sub 2. How much? A sub 2? 0.1023. And now we're going to go with B1. That is 1.3654. And B2, that is 1.649. Oh, B2 here, 1.649. Okay. And we need also C1. C1, that is what? C1? 0.0003. And finally, we need C sub 2, that is 7.509. Oh, sorry, not here. 7.509. Guys, when we will have the last disconnection, please rejoin yourself with me so we could finish solving this problem. It is important. You may have one like this in the final exam. So please rejoin yourself with me when we will have the last disconnection. So we are done with this table. Now I'm gonna calculate RW dash here.
Hocam, I think you write the wrong C2. 7.509.
509. You mean 509? Yes.
Yes, hocam.
Yes.
Yes.
Okay. So let me now calculate R dash W, the effective wellbore radius. That is what? I'm going to go with this one because the phase angle is not 0. It is 60. So A theta, this is A theta, times what? RW. This is RW. Just follow me, guys. RW plus the perforation length. Here. See? So this is RW. See, guys? Now I am going to calculate S sub H. What is S sub H? S sub H is ln RW divided by RW dash. And we are good. See? Guys, okay? Now I need to calculate what? S sub V. So what is S sub V? Let me see. Where is S sub V? Here is S sub V. See, this is S sub V, and here is A and B. So to calculate S sub V, I need to calculate A. What is A? A1 times log what? I need R sub D. So before that, I need to calculate what? R sub D. R sub D. What is R sub D? Let me bring R sub D the front of you. So this is R sub D. See guys, this is R sub D. Here is R sub D. R sub D is what? The radius of the perforation divided by 2 times what? The H of the perforation. The H of the perforation, this one, times, so close the perforation, the parenthesis times the square root of KH divided by KD. See guys, close, and we are good. This is R sub D. We need to calculate also H sub D, that is H perforation divided by L perforation times the square root of KH, this is KH, divided by KB, close the parenthesis, and you will be good. Now we need to calculate A, that is A1. See guys, that is A1, here is A1, times what? R sub D, this is R sub D, plus A2, this is A2. So we are good now. And then we need to calculate what? We need to calculate B, that is B1, times what? Times RD, plus B2, this is B2. So we are good. Let me remove this one, I don't need it. Now we got this one. Now I can calculate S sub V. So what is S sub V? See S sub V, this would be what? 10 to the power A, and here is A, see guys, times H sub D, this is H sub D, to the power what? B, this is B, minus 1, close the parenthesis, be careful for the parenthesis, R sub D, to what? To the B, okay, and we are done. So this is S sub, okay. So let me highlight S sub H, but this time not the yellow, let me put it like this, and let me highlight S sub V, and let me put it like this also. Now what we need to do, we need to calculate S sub WP. S sub WP. Where is S sub WP? Here is S sub WP. See, this is it. Let me remove this one. Let me remove that one. And what we need RW. Let me put it here in front of you. So what we need to calculate RWD. What is RWD? RW, this is RW, divided by what? RW, plus what? The perforation length. See guys, okay. So this is our RWD. Now we can calculate S sub WP. This would be what? This would be, guys, C1. This is C1 times exponential of what? C2. This is C2 times what? RWD. This is RWD. Okay. So we are good. Let me also highlight this one. Now I need to do what? I need to calculate S sub P. See guys, what is S sub P? The summation of S sub H plus S sub V plus S sub WP. See, let me highlight this one by yellow. Okay, so now we got S sub C plus theta S sub V. Now it is given to us, so we do not need to calculate. S sub D is given to us how much? It is given to us 0.5. So let me highlight this one by yellow. And we have given that this one, guys, as you can see, this one is 1, also given to us. The Darcy flow, let me highlight this one. These are, so in this case, skin factor is the summation of the 4, this one, plus that one, plus this, plus that. See? So here is our skin factor. This is our skin factor. So what I'm saying, this is the total skin factor. Is that clear so far, guys? I think it's not really big deal. You can do it. Okay.
Yes, hocam, it's clear.
Yes. Okay. Now what we can do, we need to know how much is the impact. How much is the impact of the skin factor on the productivity index? What would be the fold of increase or the fold of decrease in the productivity index? Okay. So the first thing that we need to know how much is the average permeability. So we're going to assume that the average permeability is the square root of what? The vertical permeability times the horizontal permeability times the vertical permeability. So this is the see, this is the permeability, the average permeability. Okay. See, this is average permeability. Okay. This is millibars. Now we can calculate J with skin factor and J without skin factor. Okay. So J with the skin factor is what, guys? If you remember that J with the skin factor is K, as you remember, K times what? Times H, the formation thickness, divided by what? 141.2 times mu, the viscosity, times oil formation value of factor. Okay. See, close. See, yes, no, times open ln. I'm going to assume that we have pseudo steady state. So ln Re divided by Rw, see, minus 0.75 plus what? Plus skin factor. See, this would be good. I think we need to close another parenthesis. So this would be the skin factor. Okay. And we can do it again, but we are going to remove what? We are going to remove the skin factor from the second case. So this is with the skin factor. So as you